So, hi everybody. I'm a bit surprised that the room is pretty packed. So, thank you for coming and thank you for having me here. Today, I want to talk about the mutation testing and the way we should actually take to leave the Stone Age. So, a few things about myself. I'm a iOS developer by day, and in my spare time, I'm actually hacking on compilers, and this is like basically my hobby, and this project actually my hobby itself. So if you're curious, you can find me on Twitter, and I have two blogs where I write about some low-level stuff, LLVM itself, and mutation testing also. And especially if you are into software testing and quality of software, then I recommend you to look at the last link, the systemundertest.org. There I and friends of mine, we are writing about different software, how it's tested, and so on and so forth. So it was shameless plug. Yeah, this is the outline for today's talk. I will start with the quality of software, then I will talk a bit about the unit testing, then we will move towards mutation testing. Then I want to present the tool that I'm working on, and at the very end, I will try to present a showcase, like real-life usage of this tool. But I'm afraid that I will not be able to give you like some stellar examples, but that's going to be interesting, I hope. Yeah, so I do software for about like 7 years now, I think, and I enjoy it a lot. But one thing that I'm concerned a bit is the fact that software is just like broken. Like essentially everything is broken, like browsers, compilers, operating system, games, just anything. It's full of bugs and it doesn't work and so on and so forth. So we as developers, as computer scientists and engineers, we are trying to put as much as possible efforts in for decades to improve the software somehow. And there are some ways to do it. So, for instance, just today we had a great talk about formal verification of programs. But I don't know much about this topic, but as far as I know, we are not there yet. The tooling is great, it's improving, but it's quite hard to verify C or C++ because of this undefined behavior and so on. So another great approach is fast testing. Yeah, I think it's like here like for a while, and now since we have better computational power, we can apply it more efficiently. So, but I think there is no doubt that unit testing is the most widespread technique that is used by software developers, and yeah, it comes with a nice metric as well, which is code coverage. And yeah, today I want to focus just on this. I'm not going to talk about like flaws and advantages of fast testing or formal verification, but I definitely want to talk about unit testing and its problems. So yeah, how it works in general. We have some code, and yeah, this is like artificial example just to start. So we have some function, sum, that takes 2 integers and returns a sum of them. And for this function, what developer does, he writes a code like the assertion is that the sum of 5 and 10 is greater than 0, which is absolutely correct. It's a valid statement, but it's not enough because 5 multiplied by 10 also greater than 0. So if we run this test, then we see that 0 test has failed, 1 test passed, and the cut coverage is 100%. So it definitely has some. It might be misleading. The code coverage metric might be misleading. And I see that sometimes people are striving for this number, but the code quality is not the code quality, but the test quality is not as good. And there is no way to measure it, actually. There is just no way how to assert how good our tests. So here comes the mutation testing. So I will try to explain the algorithm behind it, like very briefly. If there is something like completely unclear or like really confusing, just feel free to interrupt me and ask. I will elaborate. So yeah, what we do like normally with mutation testing, we have a program and we have a test suite. We then execute this test suite against that program, and if everything is good, if tests are passing, then we do the following. For the program, we take a mutant, we create a mutant out of the program. So we basically do some mutation on it. And it must be some semantic change. The program should be different. Then we take that mutated program and run test suite against it again. And then we check the result. If the result is failed, then we claim that this mutant was killed. This is essentially a good thing. So if you run a test against mutated program, then the test should fail. If that's not the case, then we claim that mutant is survived, and this is kind of bad. So it means that something is wrong, either code or the test. So here again, our initial example was the test and the program. So out of this program, we can generate many mutants, but I will just show a couple of them. So first one is we replace a plus b with a multiplied by b. And the second one, we replace a plus b with a minus b. Now, if we run the test against the first mutant, then it is still passes. So mutant is survived, and it gives us a hint that something is wrong. However, the second mutant was killed, and we are good to go here. So based on this example, we can derive few numbers. So the total amount of mutants is 2. One mutant was killed, one was survived. And mutation testing also comes with a metric called mutation score, and is calculated by the formula on the screen, like killed mutants, amount of killed mutants divided by amount, or like total amount of mutants, and multiplied by 100%. So in this specific case, the mutation score is 50%, and it's not good. So again, you should not strive for 100% because you probably will not reach it anyway, but you can use it just as a hint. So higher mutation score is better. Yeah, few facts, few things about mutation testing. Oh, spoilers. Yeah, sorry. So it was first proposed by Richard Lipton in 1971. I think it was called mutation analysis. So these are the same, kind of the same terms. So it was first implemented by Timothy Butt in 1980s, and I think it was for Fortran, but I'm not sure, so don't quote me on that. There are several studies, like quite recent studies, that show that certain mutation testing systems for certain programs, they could help to find bugs, like real faults, like quite high number of them, like 70 and 90, actually 90, 94, 92%, like to be more precise. But even despite this fact, mutation analysis was not widely spread because it has several problems as well as just everything. So the first problem, it generates like lots of data. For just 10 tests for a small program, you can end up with 100 mutants. And if you execute those 10 tests against those like 100 programs, then you end up like running the program like 1,000 times in the worst case. Second one, yeah, it's time consuming. Because of this, like the data, we have lots of data, we need to process it, to execute, it takes quite a lot of time. Languages, they are not all the languages, I would say, are friendly for mutation testing, because I think it's kind of easier for languages like Ruby or JavaScript, because you have just like eval and, well, YOLO. So, but languages like C or C++, they are more, they're not as friendly, because you essentially need to mutate the program, like to change the source code, like maybe AST, I don't know, then compile it, then link it together with everything and run, and then assert. It's just quite slow, though I don't have real numbers. Yeah, there is also a problem of a human test oracle. So let's say we generated lots of mutants, and we cannot just say like whether are they good or not. So we need somebody to actually look at those results and make the decision. Yeah, it also comes with another problem, but I will tell a bit about it later. So actually, and yeah, another one problem, I was surprised by that. I heard this like almost exactly this phrase, like, excuse me, but I write good tests. I don't believe it, and for me it sounds like, excuse me, but my code is bug-free, which is, well, not the case. My code is bug-free, but yeah, not in general. Yeah, yeah. So the tool is called MAL, not MUL. So with this tool, we are trying to solve some of those problems, but not all of them. And there are some things that we do to actually improve the performance and make it well, better in general. So we have kind of smart mutant selection. It means that I mean, it just helps us to decrease the amount of mutants and amount of data we need to process. And it's very similar to the second point. So we provide a means to control the data generation. So I will elaborate on it. Yes, it's complicated as well a bit. So we also utilize the runtime compilation and JIT. Particularly, we use LLVM for that. And it means that we don't need to link something. We don't need to recompile things that much. And we completely eliminate I/O, bottleneck of I/O in this case. So because of that, we are operating on the level of LLVM IR, which gives some nice things, but also comes with problems like sometimes you cannot like correspond the IR with the initial code. So they might be different, especially with C++ with all these templates, inlining, and so on and so forth. And the great thing that it is language agnostic, given that all the languages are built on top of LLVM. So if something is built on top of LLVM, then it's likely that we can use it. Yeah, so it's time to elaborate a bit on how the system works. So this is the typical program. We have like several source files, bitcode files, modules, whatnot. They have some functions and instructions. And if we just go and analyze the whole program as is, then we will find out like many mutants, many places where we can introduce the mutation. But it's not very efficient because most, like maybe not most, but big part of this code is like just unreachable for whatever reason. So the better approach would be as what we actually do. First, we try to find the actual tests, thing that are, well, tests essentially. And based on those tests, we take the call sites, like call functions. We are trying to build so-called call tree. And based on this call tree, it's like on this slide, you can see some modules, they are not needed. So we can just eliminate them completely. We don't need to compile them. We don't need to analyze them. Just, I don't know, consumes less memory and so on and so forth. So, yeah. Whereas with this optimization, it is actually still experimental. It's a bit more tricky than I thought before, and it has some problems, but it is definitely the way to go. So for example, on this slide, we took some subset of tests from LLVM itself, the target called IR tests, and we just took like 250 of tests. And before to run the whole system to process it, we needed to look at like 400 modules, and it took roughly 85 minutes. After this improvement, like cutting those like unused modules, we got like 3 times less modules, and almost it works like almost 2 times faster. But again, it is experimental. It's not in master trunk yet, but we're working on it. So here is the most complex program, like closer to reality. And here we can see that on the left, the functions on the left, they are tests, and they go some way to like via some distance. And it has some distance. So for the same subset of tests, we took distance 2. It produces the 1,500 mutants, and the real execution time that I measured on my machine took like about 1 hour, which is kind of acceptable. But for, on the other hand, if we took the whole program, then the distance is 29 for this group of tests, and number of mutants, I think there is actually a bug. It should be like orders of magnitude more, like maybe 200,000 of mutants. And approximation of like execution time is roughly 11 days, but it's very pessimistic. So in reality, it will take maybe 7 days, 6. So yeah, that still doesn't help. Yeah, and with this numbers, actually, with this mean to change the distance, to control the distance, even if it takes 1 hour, you cannot probably use it on your machine on like daily basis because, well, it's kind of waste of time. But you still can use it as like with the nightly builds, for example. And for, yeah, mutant control, okay. Yeah, there is another mean. We can select some specific tests. So let's say you have like 200 tests, but you're interested in like one or like some group of tests. And yeah, so basically you just like select one test and work with it. With like even like you reduce the amount of tests even further. And I didn't put numbers on slide, but I think the best case was like 30, 40 seconds maybe for one test. And the worst case for a group of tests, which is maybe 15 or 20, took like, I don't know, 15 minutes, 20 minutes, which is like still reasonable. And it enables like really, really fast iterations. So I think this is like the best improvement that we did so far, the best kind of invention. Yeah, so a few words about the system design, how it works in general. So this is like in a nutshell. The program consumes as an input a config file, which is just a YAML, which doesn't matter. What it contains is the list of bitcode files. Basically shows which modules, where to get modules to process. And it also like has this settings for distance and some cache and so on and so forth. So, but what the program spits out is the another config file and the SQLite file. So that another config file is reduced version of the first config file. So let's say initially you provide a config with 400 modules, and you found out that you were like used only 100 of them. The next time you can run the program with that reduced config, and you will not need to process like the 400, but rather 100. So it's kind of also improves the iterations. Yeah. We also don't provide any, so yeah, I mentioned the mutation score, but the program at this very moment, we do not provide any like short report like your mutation score is something %. Because again, as I said, I believe that we should not strive for numbers. We should just use them as a hint. And what we provide instead of this is the SQLite file, which contains information about just everything. And it has the advantages. So if I run something and I get results, I can treat them in any way I want. And I don't have to restart the program again, wait like an hour or a week, and just, again, iterate faster. So this is, yeah, the program from the like outside user perspective. So internally it consists from several modules. One is kind of core. It has just a driver that well controls the basic system. It has a reporter, and it will be likely extended or replaced in the future. So instead of SQLite, you can report to the output or whatnot. One essential part actually is mutation operators. I didn't talk about them before, so I will just briefly explain what's that. So every mutation tool, mutation testing tool, they have some mutation operators. These are things that, like kind of rules that describe how you change your program. So it could be like replace plus with minus, like remove void function, or replace like a negate condition, for example, or I don't know, like skip the whole loop, for example, or like anything you can imagine. There are also some studies that do the mutation operators for Java, I think, and they go in further and they change the class hierarchies, like they inject some classes, remove, and so on, just to screw the system up even more. Yeah, the second part is also like straightforward. It's a tool chain. Maybe it's not the best name, but it just like JIT compiler from LLVM and the object cache. So once we run the program once, we usually don't recompile biggest part of it with the next run. So it's also improves the speed. Yeah, the most important, in my opinion, the most important piece, the most important thing is the test framework. Basically, this is the one thing now that is abstract because it can be like Google Test, for example. If you want to run the tool against C++, then we have driver now and like all this infrastructure for Google Test. It could be also like XC test, for example, for Objective-C and Swift potentially. And just, I think 2 or 3 days ago, we merged the initial support for Rust. It's not production ready. I mean, the whole tool is not production ready, but the Rust, you can just take it and apply on any project, but we'll get there. Yeah, so kind of showcase. Initially, like a month ago, I wanted, when I was planning the slides and so on, I wanted to run the tool against the LLVM itself and gather some results, dive into it, and find something, probably something interesting. But the problem that I face that to actually to actually make sense out of those mutations, I need to know the domain of the tool very well, which is not the case, unfortunately. I don't know the most part of the LLVM, like AP float and some other stuff. But the results are available online. They might be cumbersome and unclear and maybe cryptic because I'm in this context and I do understand everything there, but it's hard to understand. Like it's hard to know for me what people may need. So if you're into it and if you are interested, you may take a look and give some feedback. I would really appreciate it. Yeah. So again, some numbers for example that IR tests. Yeah, you can see here the mutation score is 43%, which is quite low, and I actually saw quite a few places that can be improved, but again, I cannot just like do it easily and fast. I need to dive into this matter, which I didn't. And the same goes for ADT tests. The mutation score is a bit higher, 66%, but it is still quite low, I would say. So what I did instead, I took the one part that is quite small and the code there is quite straightforward, so even I can understand it. The triple tests, I don't know if you're aware what the triple is, but it doesn't really matter. So just some group of tests. And yeah, the mutation score is quite high, but I still wanted to see what's going on there. And first thing I found is this kind of tests. So we have triple, we change the architecture, and then we ask for, well, then we assert that some, like in this case, like other architecture, like based on that initial architecture is like exactly as what we need. So what's happening behind the hood under the methods like get little endian arch variant, there is just like huge switch statement, and that just maps things together. And what we did, we basically started like removing switch cases like one by one, and we found that many things they just can be removed and the tests are still passing. So in this case, it just means that we just need to add like to add more tests. Yeah, slides I think switched, but okay. Yeah, so one could argue actually that this case can be found by code coverage, and this is like absolutely true. It will be there, I'm pretty sure. But the nice thing about the mutation testing in this case, that you get a report like this one, and you clearly see like what was removed. Like let's say you remove this case, and you see like which tests were affected by this. So basically, what tests you need to extend to improve to cover this case. And it took me like just the whole flight from Berlin to Brussels, like 1 hour maybe, to improve this a bit. And yeah, so I just like I covered all the cases, switch cases that like enum cases that were not covered. And yeah, I committed this, I think, last night. So it's in trunk now. The second one is more interesting in my opinion. So yeah, the test is like straightforward. We set some property of an object, and then we assert that property is exactly like equals to what we just like used. But this test actually will pass if we just comment out this line. Just because the elf is default value. So there is no, I mean, yeah, so what mutation did in this case, set object format, the body of the method was kind of removed like completely, and the tests were still passing. So also what I learned from this very specific example, so if you have situations like this, then it may make sense as a developer to cover like at least two cases, and then it's very likely that you're good to go and you are not asserting default value. So again, I just like added like 2 lines and also committed it.
As a check for default, initialize to not default in every test.
Can you repeat, sorry?
You had a test case which tests the default.
Yes.
And now you have claimed this as truth.
Yeah.
And then in all the other test cases, you initialize to something which is not the default before you do the thing.
Yeah, this is how it should work, but this is not how it works. Yeah.
Well, in this case, actually, you should have replaced the Mac O as first and the alpha second, because you still don't need the first set object format.
So I think it's a bit trickier. Okay, I cheated a bit. Okay, so the elf is not like default, like is like completely default. It's based on, so it's default for Linux.
On the arch that you run, yes.
Yeah, it defaults on Linux, but it's different on OS X, and even I run it on OS X machine. The triple initialized to default value, like it, when you give the empty string, it thinks that it's Linux machine. No idea why, but that's how it works.
Don't try to understand the triple.
I didn't have this goal at all. Yeah, so another example, it's not like the code exactly. I think I found it in IR tests, but I might be wrong. But the idea is that you have something like if something, then we use slow version of an algorithm. Otherwise, we use fast version of the algorithm. And we have some tests. And if we basically introduce some mutation and we flip those branches, then the test still passes. And again, one could argue that this is like fine, but I would say no, because the only notion that something is slow and fast is like basically the name of a function, which is like not always the case. There might be just some comment, and it might be true as soon as like the developer like wrote this code in the first place. But like next year, somebody fixes a bug in the slow version, and it becomes not that slow maybe. And somebody else fixes bug in the fast version and it became slow. So in this case, there should be some tests like to measure like performance, how slow, how fast. Maybe they are like not, maybe they are the same by performance and there is no need to write this code at all. Yeah. I think that's pretty much it about this showcase I wanted to show. So as I said, the tool is still in progress, and we have some open questions. The first one, and the most important, I think, the most kind of cumbersome, is the integration. So since the tool is working on the level of LLVM bitcode of IR, we need to get it somehow, from somewhere. And to get the bitcode for tests from LLVM, I needed to use CMake, then Ninja, then like bloody shell scripts with set, grep, and so on. So it's just not straightforward. If you want to use it on your project like plug and play, we're not there yet. So this question is still open, and we are trying to find the best way to do this, to improve the thing. So another kind of problem is UX. It's still not clear, again, like how to do this like properly. So what we did initially, this SQLite file, and I wrote like bunch of Ruby code to generate this like pretty and nice HTML, and it really nice and it works for me, but I don't know how it works for other people. And again, the question is still open. We are trying to find a way to make the system usable for people. So another one. I think it's not the question anymore since we merged support for Rust. We were talking about like which language we should try next, because right now the system works fine with C++, but I'm afraid that the current system design can be biased by C++ itself. So we wanted to take another language and to make the system kind of flexible and, well, good. And there are obviously many unknowns. So we don't use this tool in production yet. We don't have any users so far. So if you think that you're interested into it and you want to try, then I urge you to contact me, and I would be more than happy to help, like free and so on, like just for sake of the tool. Yeah, so the project is available on GitHub. It's open source. It's like we're developing it, well, in an open way. So if you have some questions or you want to give it a try, and I will gladly provide you support for this, and just drop me a line at alex@lowlevelbits.org. Yeah, and for some updates, you can either follow the project on GitHub or follow me on Twitter, and I'm posting the updates on the process. Questions? Yeah, please.
Do you find that these tests drive you to like over-specified tests, like testing your add test will always return 5 as opposed to like testing the specification of the method versus the actual implementation?
Yeah, so I think yes. So I found one test. It's quite lengthy, and it tests some quite like another lengthy function, and there are maybe like 10 assertions in this test, and they all check whether the method returns true. So it doesn't check it just checks like basically one case with different inputs, but one case. So yeah, does it answer the question? Okay, thanks. Yeah, please.
What will happen if after lengthy changes, the code is misfunctional? It's not compilable, doesn't work at all. Is
So.
it good or bad?
I think it is compilable because we control this stuff, so we try to make it compilable. And we run all the tests, and all the mutants they run in child process, and we control that process. So if program doesn't work well, it crashes, then we know that it crashed. If it happens to have like some infinite loop, then we also we have timeout, and we just like catch this as well. Yeah.
What will be the result? Is it good or bad?
There are some debates on this. In my opinion, it is good. I mean, the program is broken then. So we broke the program. So I think it's a good thing. But the opinions are where I don't know how. Let's go from left to right.
Do you do anything to try to not make mutations that make the LFM IR undefined itself? Like there are some bits in the IR where it says that if you do this, like the behavior is undefined. So do you introduce mutations that have that sort of behavior, or do you try to not do that?
So we barely control this aspect. We just again like make change and like YOLO. That's it. That's our approach. Yeah. So.
Yeah, my question actually ties into the previous question insofar as I'm wondering, in say C++ or D or Rust, there's quite a bit of stuff that's guaranteed on a type system level. So where you could do an IR mutation and see that the mutant survives, but where you know you couldn't have possibly made a mistake in a program.
So we are trying. Okay. So the question is whether we can.
I mean, maybe some memory corruption. In that case, of course, it would crash and you would say, okay, the program is broken.
Mm-hmm.
But, on the same level, you could think of mutations that you kind of just type in the source. And for an AST-based tool, you also couldn't, make that mutation compile.
Mm-hmm.
If you just turn and add into a sub on the IR level, it seems like you could introduce many mutations that aren't necessarily valid.
Yeah. So the question is whether we introduce some mutations on IR level that are not possible in the source code level. Is it correct? Yeah, more or less. So we are trying to not do this, obviously. We don't have any guarantees on this, but we are trying to avoid some mutations. We have some like filters and some heuristics to not do this. So for example, in case of C++, there are like lots of code is coming from the standard library, for example. It just was inlined, and it happened to be like the client code, basically. But if we mutate it, then it doesn't make any sense, because it's unlikely that you have a problem in, well, in standard library. That's not what I wanted to say, but you get it. Yeah. So there was another question, I think. Yep, please.
Yeah, so I got the impression that maybe for some projects, if you want to get a better mutation score, maybe you start adding an order of magnitude more tests. Do you have any idea on how much pushback you would get then? Every time you want to make a change, then for every line of code you change, you have to change 10 times more lines of tests, and it slows down your project because of that.
Well, then that's
Would that be a
badly
pushback?
written tests.
Yeah, but
I don't know if the mutation score is good, it's good tests.
So
The
again,
mutation is good, but then those tests that he added should never be changed because they should be right. And then if they're not, it's his fault.
yeah.
I'm just wondering if there's any experience by anyone in practice or real
So
life.
I don't have any experience in practice that can contradict or approve your statement, but it can be, yeah, it can be. So yeah, please.
the execution or the selection of mutants, is this scheduled kind of statically up front where you generate the threat, or do you do this as the testing progresses? So you could, for instance, look at, are we reaching a threshold in mutation score, in which case there's no point in running much longer?
Well, actually, no, that's a good idea, but no, we do, so the phases, like the first phase is analysis. We gather all the information about the whole system, all the mutation points, mutants, and so on, and then we start generating them and executing. So that might be actually, yeah, that might be a good idea.
Because I, as a comment, I could imagine that using a variety of mutation operators might find a lot. You can go shallow and very broad. And that might be enough for a program which is not well tested. Whereas if you have a really well tested program, you might need to go very narrow and test very obscure things.
Yeah, that
Only works
might be
if
the case.
Changes are cumulative. If they're not, then you may be a cluster of many good changes at the end that you cut short because you weren't changing any at the beginning. So
Yes. So there are challenges. But
yeah.
Yeah, but there is like always the trade-off. Yeah, you can miss something, and yeah, please.
So what can I learn from a bad mutation score? Should I change my tests or should I change the code that I'm testing?
You should take a look and make a decision then.
Okay, so I
yeah.
have to understand the code.
Exactly, yes, yeah. That's the problem why I didn't manage to give nice analysis based on LLVM itself, because I don't know many parts of it. So I could not understand what's wrong with test or code.
That's
Yeah.
it. No, we have
Let-
only 2 minutes to switch. Okay, one last question.
Sorry, yeah.
Do you have any plans for parallel execution or stuff like that?
So,
For practical,
not yet. Well, we do have plans, like obviously, but they are like long-term, not something that we'll do soon. Yeah. So, thanks for questions.